I'm Jonathan. I think most people who are regular here know me. And I'm going to be talking about how to use modern C++ to eliminate virtual. I think the first thing to kind of ask here is like, when is virtual useful? Like, what features are we trying to develop solutions for, right? And I could come up with three specific cases. One where the first case is where you need an implementing class to provide a specific interface. So you implement a pure virtual interface, and then you have derived classes that will have a certain structure of function calls, return types, etc. The next is adding configurability to objects. So if you have an object and you want its behavior to be able to be changed by changing out an object that it owns, which it'll call into. Virtual is frequently used for that. And also holding multiple different derived types. So you hold a pointer to base, and then you can have multiple types of multiple objects of different types in a single container. This sort of thing is particularly common in like game development worlds, where, or at least many years ago. I'm not a game developer, so you'll forgive me if I'm a little bit off here, but where you would have an entity, and that entity would represent anything that could move in your world, and that entity would, the entity class would just have position information, and then you would have like weapons, and the weapon would inherit from entity and take the add damage information, and then you would have players and enemies, right? And then you could have a single list of all the entities, and if you wanted to update your game state, you iterate through the entity list, right? So those are the kind of use cases that we need to be thinking about to do this. So why would we want to replace virtual? So if we replace virtual, we get less indirection. Usually to take advantage of virtual, you're going to be dealing with pointers. Especially, you may not want to be dealing with pointers. You may have an object that you own directly, and you're introducing a layer of indirection there simply to hold a base class instead of holding the object that you actually want to hold. It allows you to capture system properties more statically. So you can define your system more at compile time if your types are more tightly constrained. You can improve performance. I'm not going to get into that at all tonight. I think that's probably a talk on its own. But if you want to kind of start picking at the edges of that, there's some really great blog posts on Johnny's Software Lab that convinced me of this pretty well. I also wrote a couple micro benchmarks around the sorts of things that I'm presenting tonight. And I was seeing somewhere between a 2 and 4x improvement in micro benchmark. Whether that carries out to a real application, I haven't done enough investigation to say. If anyone does, I'm certainly interested to hear results. Please talk to me. And also, because we can, I think it's just a cool thing to explore. I think it tests the limits of the language. It makes us ask, it makes us challenge ourselves just as developers. And I think that's, even if you don't end up taking any of these approaches, I think that the sort of thinking that you do to get there is particularly valuable. So let's, without further ado, let's get into some code. So the way that I've structured this, every time we're going to start with the virtual implementation, and then we're going to kind of work our way through developing the same characteristics without using virtual at all. The nature of this is kind of that there's one really big step right at the front. If I lose you, please feel free to shout out and ask for clarification. I absolutely cannot see the forest through the trees on this at this point. So here, our first case, right? We want to bind an interface. So we have a pure base class. It requires that there's a function called func that returns a type called int, and then we have a class that inherits from that foo, and you can see it implements func and has a return type int. and has the specific implementation, which here returns everyone's favorite number 42. And this is roughly what this would look like in the wild, kind of in concept, but in reality, what you end up with actually is, because you're going to be holding pointers to all of these things, and because you're dealing with inheritance, you need a virtual destructor. Because you need that virtual destructor, you also then need to, default assign everything else to stay within the rule of 5. I think this, if you don't know what you're looking for, this makes things a little bit more confusing, and even if you do, it makes them a lot uglier.
You don't have to do that in the derived class, just for the record.
It depends on how you're using it. Sometimes you do. Anyways, but yeah, so
not in this example, you don't have to.
That's correct. Once you start creating pointers of derived, then you do. So just kind of for some scale as to like how bad of interface this is, I wrote a bunch of like sample patterns while I was developing this talk, and in that repo I ended up defining all of this as a macro, which I think is about as bad as things get.
Wait, I'm sorry, you said that you practice this without questions, so now I'm going to go ahead. Why would I have to, if I have pointers of derived, have to do this in the derived class?
Shoot, I don't remember that offhand. I just remember being frustrated about it.
You should not have to, because the virtual destructor is inherited from the base class, and the rest of it falls out from there.
I think it may be non-mandatory, but it might come out with a compiler warning.
It does not if you don't mention any of them. I just had this come up in a code review that I did for.
Oh, okay. Yeah, so perhaps you only need one set of these. I'm certainly not confident. The point stands, though, that it induces a lot of extra code that functionally doesn't do anything, right? You're just saying a bunch of things are what they would be by default, except that you've added the virtual keyword in one place. So if we want to get rid of this, right, we can take that same foo class that we have, drop the inheritance, and bind its interface using a concept. I just want to make a note here, just for people following through for the rest of the presentation. I've started naming my concepts as like C whatever, the same way that we do types as T whatever. If you see, C foo, T foo, going forward, that's what that means. Just keep that in the back of your head. I think it'll help keep things understandable. So we combine this same interface here, right? We say this says the exact same thing as our base class, right? It says we have a function on the object foo, and it returns a type that's the same as int, which is int. And then if we want to here, we can statically assert that foo is of type C foo. I've seen this done in like inline in like headers or whatever. I would suggest that this is actually a test, and that you should put this in your test code, just so that you don't have that static assert constantly being assessed, etc. It should remain true. And then where you need it, you should apply it to your interfaces, not as a constraint on the class itself. I also think it's interesting to note that we can get additional flexibility out of concepts that we don't have with base classes. Here I can say that I want the return type to be anything that's an integral, whereas with a virtual interface, there's not a good way of doing that. So just to kind of put these side by side, look at what it might look like to call each of these. With virtual, we have to store to a pointer of base type, and then we create the derived type. So that call ends up being kind of nasty, in my opinion. Whereas without virtual, it's just a basic object instantiation. Anyone got any questions before we charge onward to our next example?
Oh, I was just gonna mention that there's you can put the requires. I'm posting to a link on the chat. You can put the requires somewhere else so that you don't have to put the static assert. And so it gets to become part of the derived class.
I'm not sure I follow.
I'm posting it in chat.
Are you talking about like using like constraining on the class that consumes a foo?
Yes.
Yeah, we're about to get there. Don't worry. Anyone else before we charge
Oh,
on?
no. Not the class that consumes the food. Like
It might be
before
helpful if you go back to where you actually had the static assert. Okay.
Yeah, so I'm posting something in chat where the foo you can actually put it requires in the constructor, and so then you don't need the static assert.
Okay, I'll definitely. I don't know. How do I get to chat when I'm sharing? All right. Whatever.
It probably requires being in dual monitor mode. Might require, or it's the banner at the top of the share window gives you the widgets.
That's on my other screen. I wasn't even.
Yeah.
Maybe we can just talk about this later.
Yeah, I'm gonna open that. Oh, that didn't work. I'm gonna open that so that I can look at it later. Okay, cool. Any other questions before we continue? Cool. So the next case is owning a polymorphic type, right? You have some functionality that's configurable, and that's going to be configurable based on a type that you hold. So in the virtual case, you have your base class, your interface type, and you're going to take an object that has that interface type, so that you don't have to care about its derived type. You hold on to that, and then you do everything else in terms of that. So what we can do with, as of C++17, we have CTAD, right? We can deduce the type that we want to hold based on the input type, and simply hold that type. But as I'm sure some of you have noticed, we can make some improvements here, right? Right now, this doesn't constrain that the interface of tfoo matches foo, whereas in the previous case when we had foo interface, that guaranteed us that we would get a compile time error if we didn't inherit. So we can add a concept constraint to the template type, and now I would contend that this does everything that the previous implementation does, with the exception of runtime reconfigurability. So let's talk about runtime reconfigurability. So we're back to our virtual implementation here. You'll notice we've added the method setFoo, and that's just going to take a new foo and replace our old foo. Same thing the constructor is doing. Nothing interesting there. To implement that without virtual, we have to make some not insignificant changes. Our storage goes from being a tfoo to being a variant, and we have to take a list of the types that we might hold to service that. I would personally contend that this is probably a code smell. If you need this sort of runtime reconfigurability, I can't think of a case where this doesn't seem like a class that's doing too much. I would prefer that changing the behavior of a class, that it be configured at compile time and then left alone. I think it creates unintuitive behavior. If anyone has cases where this might happen in the wild, I'm super interested to hear about them. Please talk to me. One thing that you'll note here, we introduced a new concept. So there's a new concept here. It's called same as any. We're using that to constrain the type on setFoo, and we just want to make sure that as well as the constructor, and we just want to make sure that the type that's coming in is one of the types that was provided. You will get a compile error with that when you try to assign to the variant, but I think the concept error is a bit easier to read. But again, probably don't do this. This is probably not the way you want to go. But if you need this functionality, this is how you do it.
So I want to clarify what you're saying here. You're saying what's the code smell?
The code smell is the runtime change of behavior of bar. I think that there's probably a case for like something like compile and init time change. Like I think that happens fairly frequently.
Mhm.
I don't know of a case offhand where changing that at runtime is sane.
Have you ever done GUI development?
No. I was
Okay.
wondering if there might be something in there that where that becomes relevant, but I wasn't sure.
Pretty much any case where you have to drag and drop elements in a GUI uses that kind of runtime behavior change.
Can you link me to some of that?
That's probably one of the Gang of Four design patterns, is it not, Jason?
I honestly don't know. I'm only on chapter 1 of design patterns. So.
The book's
Yeah.
25 years old plus, but that's okay.
But it's literally how any GUI toolkit is designed. So it's if you ever need to like drag a component from one thing to another and drop it in another place, that's the classic use case for this kind of behavior.
And the usage there is when you drop it in the new place, it's like its new spot is.
Its new spot is you have no
Yes.
idea what was just dropped in there. It's something that knows how to draw itself. You tell it what its size and shape is. It knows how to draw itself in that confined space. It knows how to receive mouse events that you then forward to it, but it's all virtual interfaces because you have no idea what the user is going to do at runtime there.
Okay, that makes sense.
Okay.
Anyone else have cases where this might be useful?
Perhaps a state machine.
You can certainly do state machines without variant.
Yeah, I've seen too many compile time versions of state machines to have that to be the top thing of my brain.
One thing I did
That
notice
we're
about this,
brainstorming here.
Oh, right. Sorry.
one thing I noticed about this slide is presumably the intent is that the T's are all different, but that's not a compile time requirement here.
Yeah, there's a lot of constraining that you probably want to do on these types. I've left a decent chunk of that out just because it's slideware. But yeah, those sorts of things are definitely the kinds of things you should be considering when you're writing this sort of design. Any other ideas for what places? I'm particularly interested to see if anyone can poke holes in this.
The
All
only
right.
cases that I know of is when a human is involved. I mean, a user.
That makes sense.
And line 11, I would not use variance assignment operator. I would use the in place. I would use the type based or index based constructor for the exact thing.
Stupid in place T kind of thing.
Yeah, because the assignment is too loosey goosey.
The fact that in place T exists it troubles me. I understand why. I don't like it.
Well, it's not necessarily that you need to construct in place. Like if you get a copy, fine. Like that's the semantic.
Right.
But line 11 will pick the first thing in the variant that can be assigned.
Oh yeah,
right. Which isn't necessarily what you wanted.
Yeah, that's a good point. I was trying to maintain parity with the previous example, but you make a strong point. Okay, so let's talk about usage. For the case with virtual, you've got that make unique floating around. I think that makes, it's just one more thing to trip over. Whereas in the case where you don't need runtime configurability, it's just simple objects, everything deduces. In the case where you do have to specify the type lists. We'll talk about a way to make that even nicer through the next example. But before we do that, anyone have any comments, questions, anything on this example? Cool. Okay, so now we have to store multiple types, right? So in the virtual case, this is straightforward. We take a value, we just put it on a vector of pointers to base. I assume everyone has done this plenty of times. It's pretty straightforward. So to replicate this without using virtual, we need a couple of things. So we need a list of all the types that might be stored. We can get that pretty trivially with a type list. We need a container that can hold many different types simultaneously. I bet some of you are thinking vector or variant rather, but the actual thing we're going to reach for here is tuple, because we're going to need more than one simultaneously. And we need a container that can hold multiple objects of a single type. Here I've selected vector because it's a good default. If you have a use case for something like an array or a list, that would work equally well. Select this based on your use patterns. So here we've got the tuple of vectors of t's, and then we have a store function. That store function is going to do a get and just find the vector of the type that was passed in. And then we're going to push back a value to it. I will note there's a limitation here. In the previous, in the case with virtual, your ordering is consistent. You know, the order that you put things in is the order they come back out. Here, you're ordering information external to the type of that you have is lost. So if you have, you know, T1 and T2, you know the order that all the T1 elements went in, you know the order all the T2 elements went in. You don't know where any of the T1 elements went in relation to the T2 elements. So this is our basic implementation here. But again, we've got some opportunities for improvement. We can add a concept to the class types, and that'll ensure that we get a nice, pretty concept error message instead of, you know, failing when we try to get the vector, or, you know, however that happens to fail in our particular use pattern, which will be much more difficult to diagnose. We can also constrain the type of store, ensure that it's the same as any, use that same as any concept that we discussed before, to make sure that the type T is the same as one of the T's. So getting into our use patterns here, we have to make unique again for different types on when we use virtual. Without that, we can just assign directly, but we do have to say what types we might put in. I would argue that, you know, line 2 is better than line 7. And so, you know, ask ourselves, how do we close that gap a little bit? And we can do that with an alias, as long as you know all the types. I expect that would you're probably going to be instantiating a lot more than one bases in most cases. And so you can hide that behind an alias, and then you just, you know, when you add a new type that conforms to that concept, you can just add it to that list, and everything is nicely centralized. Any questions here before we move on?
There's a comment from Charles that this is an entity component store in a nutshell. And I was also just thinking that it gives a very data oriented, like it's like an automated data oriented design kind of approach.
Yeah, that was actually the kind of where the idea for this came from. Was I was struggling with, I got on this bent a while ago where I really wanted to, like, you know, re-implement a bunch of things from previous jobs, but do them better. And I was really struggling with, you know, coming up with a pattern where I could store multiple types. And I was listening to a podcast, and someone mentioned, like, decomposing entities into, like, a list of weapons and a list of players and and I was like, oh, like, I need to do that, but I need to do it generic. Like, how do I do it generic? And, you know, this is what fell out of that line of thinking. So yeah, good eye.
I just want to add that if you squint, this is a database in a nutshell. Because everything's just rows.
You have to squint pretty hard.
Yeah, pretty hard. But I just love how database theory from the 60s is actually just as relevant today as for high performance programming as it is in the 60s.
Yeah, and this is, so again, I don't want to talk too much about performance because I don't have the data to back it up, but this is in my, like, very limited, you know, kind of shooting from the hip testing. This is where I saw the greatest speed up. So
Just an aside, if your little graph is accurate for the number of slides that you've gone through, I think you might be moving a little faster than you intend to be moving.
Oh, don't you worry.
Okay,
It's
fine.
it's about to get slow.
All right.
Plus the bonus slides. The
Yeah,
full set.
yeah. Well, so we're at our fake ending. The real ending. Anyways, we'll get there. So let's talk about what we've learned so far and just kind of try to solidify some of these concepts. So C++ 20 concepts are used to bind interfaces. So we've got that use case covered. If we need compile time configurability, we can do that with deduced class templates. And if we need runtime configurability, we can do that with variant. I would really argue for the limitation of that. There are performance concerns around variant that I think are if you can avoid it, I would encourage you to. So, and then if we use our type lists, carefully, we can get statically typed storage of just about anything. And I think this is kind of like one of the core arguments here is that it's rare that you don't know all the types that might be in something, that a given thing might hold at compile time, right? I think that knowledge is nearly guaranteed. And then our last point, which I did out of order, is that you can use variant. So I'm going to make a bold claim here. I think that as of C++ 20, if you're building your binaries from source, you don't need the keyword virtual. If anyone has an argument against this, please talk to me. I'm interested to hear what you have to say.
User extensibility of the library, perhaps, if you're providing a
Yeah.
library.
I'm using a GUI library right now where really the only way to make it possible is that I have to inherit virtual functions. Totally agree with Ashley there.
You couldn't implement a concept?
No, because they have a vector. They have to know what their children objects are in a specific order because they have to know how they need to be displayed in the user interface.
Okay, I'm not sure I fully grok that. How big of a tangent is this?
Ashley, go for it.
Yeah, probably large. But I was thinking an even simpler use case, which is, I've got some library that implements an interface which takes a virtual base class, and I can provide my own derived objects into it, and it can work on it. So I'm trying to think of a good random example, but I can't off the top of my head. But
well, you could constrain that library on the concept, and then just require that the pass thing is in a particular shape, and as long as your interfaces are generic and you're compiling from source, right? Like if you're not compiling from source, this is where the issues come in, because you can't instantiate your templates in advance. But as long as you're building it all from source, I think that
when you say source, do you mean sort of effectively header only libraries?
It doesn't have to be, but
yeah,
it does end up being.
Effectively, yes.
Yeah, because if you can't, like if you've got a, so for instance, in the application we're building, we have a whole series of small libraries that we then all plug together into something. They're obviously built independently. So if the pieces are built independently and then linked together, the individual pieces won't know all of the global types, and you can't.
You can play if you really want to. You can play tricks where if you know the types, you can ensure that those templates are instantiated. But yes, like your build does get more monolithic in exchange for the benefits of this approach.
It's also the use case of loading anything from a DLL.
Yes.
Basically.
Yeah, that I previously I realized that use case. That was the one that I thought of, actually, courtesy of Ben. And that was why I added built from source.
Right. Yeah. So if you have a user extension point and they build your entire thing from source, so that you can say, well, I know that you only have 10 widgets right now, but I'm also going to give you 3 more widgets that you might want to display in your user interface. Then hypothetically, I might be forced to agree with you.
You could, in fact, if you wanted to, bundle a JIT compiler in your binary.
That, yes, hypothetically.
I feel like squinting even harder at you when you say that.
Where are we going to get a compiler?
Security sad.
Yeah, you certainly open up some very interesting attack vectors.
Like virtual doesn't seem so bad when your solution is include a JIT compiler in my binary.
Yeah.
Well, so Swift, Zig, and R all include compilers, C++ compilers now. Just thought I'd throw that out there.
I think it's also worth noting that the case that you guys are describing is like predicated on your user extending your thing by writing C++, which I think is probably a fairly limited use case. Like I think when I've seen this, it's mostly been like Lua or some interpreted language that you then bundle in. So if I think suggesting
I am literally
compiler into your application isn't too far out from what people are doing in a large number of cases for user configurability.
I'm gonna sound like a broken record here, but literally every GUI environment, user interface environment, uses virtual for these reasons.
No, yeah, and I mean that makes sense. I'm not saying that virtual is a bad decision. I'm just saying that it's not required.
I'm going to give you 2 examples, and one you've already stated, which is the DLL or the dynamic loader. Almost everything we write has a dynamic loader in it because it's how we compose things, and it actually really does help with like compile times. When you have a huge compile, if you can break up all your little pieces to be built in parallel. And then also like being able to distribute binaries. If you don't want to build the world and you want to be able to distribute binaries, then virtual becomes a friend of yours.
Well, if you want to distribute binaries that are extendable by your end user.
Yes. Well, you want to distribute binaries as a library producer that people will then extend.
I've always been annoyed when that's been the case that I've dealt with personally.
Maybe you don't have nice enough infrastructure.
I think the operative word on this slide is required, right?
Yes.
I think the claim that John's trying to make here, sorry, I don't want to put words in your mouth, John, but I think the claim is that from C++20, the static machinery is finally as powerful as the dynamic machinery in that we can constrain interfaces, we can have collections of differing types, etc. The claim is not that you may have other reasons you want to do virtuals.
Yeah, and in particular, if you want to distribute things that are not built from source, like you guys have cited a number of good reasons why you would include virtual, and I totally grant you those. They definitely make sense. If you're trying to squeeze every last drop of performance out of something, you may not want to take that approach, right? Like it's one of the many trade-off continuums that we as software engineers have to deal with.
I would posit that it's a lot more common in the library development world where you distribute binaries.
Yeah. I mean, I certainly, I can't speak for every person writing C++, right? Like, but I think, as Ben observed, my point here is that there are cases where previously virtual would have been required, and it is no longer required. And and
it's pretty cool.
Yeah, and it's I don't know. I think we're about to go have some fun with that. So if you guys, I don't want to squash this conversation. This is super fun, and actually, basically the whole reason I wrote this, I'd put this presentation together was to have this conversation. But
the other example I will give you, which you have a lot more ground to stand on, is than the dynamic loader, is dependency injection for testing.
I was just gonna say that.
Yeah, like
you.
Oh, where's Chris? Is Chris around here anywhere? Where did Chris go?
Yeah.
So that actually is exactly this case. You just make your test, whatever dependency you have, you inject it as a compile time dependency. I do this.
Yep,
I do this every day.
But then you have to build the library from source with your test.
Well, you should be injecting a mock, right? Your real use case takes the actual library. Your fake use case takes the mock.
Yeah.
Wouldn't that require your mock to be in your type list?
If you need it to be runtime configurable, yes. But you could imagine. Let's do this case, right? Like line 6 here, you could imagine defining a different bar for your test cases versus your deployed code. Because really what you're trying to test is not the types in that type list. In fact, you're explicitly not trying to test them if you're like
injecting a mock.
Well, if you're decoupling your interfaces, right? You're explicitly not trying to test those things. You merely need them to provide some very basic functionality, so that you can test the logic that lives in bar, right?
Yeah. Yeah. That what I meant to say is that like you did provide examples on how you could go about doing that.
Yeah, and if like for testing specifically, if you're not doing this, I would encourage you to like try it. I think that's an amazingly powerful pattern.
But
okay,
if you have like 2 modules that wanted to contribute their types to the type list, is there do you suggest a mechanism for doing that? Like what's the place where everyone contributes all of their types to the type list?
At some point you have to define what we're calling foo storage T here on line 7. I would suggest that everything that you want in that type list, you include in the file that defines foo storage T, and then just include that file everywhere.
So you'd need a hierarchy of modules. You couldn't have 2 peers contributing.
Well, I guess like fundamentally, like somewhere you have to know all the types that Baz could be. So you like, I guess when you say module, do you mean like C++ 20 module?
No, just independent code bases that are different sets of widgets.
Yeah, at some point you have to have that glue code, right? And I would say at that glue code layer is where you define your type list. Because like underneath it, at some point you're going to have to like know all those types. So you just pull that forward in your dependency graph. Your include dependency graph.
This just reminds me or makes me think of the idea that virtual inheritance is an open set, whereas what you're describing is a closed set, and that's just a fundamental difference between it. Unless you can show me how it could be an open set.
So I would actually make the opposite argument. I would say that virtual inheritance, by virtue of being based in the type system, is a closed set. It's just a closed set that the compiler manages for you, whereas here you're managing it yourself.
Well, in the discussion of compiling it, putting an interface in a binary, and then using that library elsewhere.
Sure.
That kind of is one of the reasons why I would argue the opposite. But
that's a fair point.
I mean, I think the end of that argument is that at runtime it's a closed set. Yes, it is closed at the point where you compile it, and in one case you compile it once, and in another case you can compile pieces.
But it's still not closed at runtime because you can load infinitely many DLLs and keep adding new things to that set.
Yes,
those DLLs were closed when they were compiled. Is the point.
Okay, sure.
Like,
Yeah, like
But from the point of
fundamentally,
view of your library, it hasn't seen those types. It doesn't know what it's operating on. So, from the point of view of your pre-compiled library, it is open. Right? It doesn't really know anything about what you've just plugged into it.
well, sure, but it's closed in the conceptual sense that like at some point there will be, at some point there is the list of types is not ever truly infinite. You could with some effort know the entire list of types, and if that effort is great, then this approach doesn't make sense. If that effort is small, then you may want to consider the performance gains that you would get from taking something like this.
You can know the list of sets as an application developer.
Sure, but you can also, as a library author, write generic machinery that takes that known list and does all sorts of fun stuff with it.
I mean, that actually just to me, that just sounds like the library developer says, I work with these types and these types only, which is a different thing to say than I can work with any type at any time.
It's I work with these concepts, and any type can, there's an infinite number of types that could satisfy a concept. Right. That's where like binding your interfaces on, I take any type, right? Like so we're going from here to here. That's where you significantly limit your set, but it remains, functionally infinite in terms of what you could be instantiated with.
Do you have any ideas for how to preserve the order here if you wanted to?
Yes. But only bad ones.
Vector of variance instead of tuple of vectors.
Yeah, the easiest way to do it is a vector of variance.
Yeah, which is that's not a runtime gain over virtual.
Yeah, I was gonna say, which if you're doing that, like you should probably just use virtual. Like you're pretty close to have implemented your own like vtable at that point.
I think it actually is considered a vtable that's implemented by the compiler or by the standard library implementers for you. It's a jump table. It's exactly the same thing, but you might save a pointer in direction.
Yeah, and at the point that you're milking that sort of performance out of an application like this, if your concern is truly performance, think about your architecture. Try to get your architecture to have more tightly constrained knowledge about the types when it comes time to like assign or access or wherever that need is arising from. All right, you guys want to have some fun? We're going to implement a multi-type vector. I've cut this down for time reasons. We might have to cut it down a little more. So if I'm skipping through stuff, you guys will have to forgive me. So I just want to start out by complaining about a feature that isn't in C++ in case someone feels motivated to write papers. It would be really nice if here on line 1, I could specify a user supplied concept. I don't believe that exists. I don't think there's a way to concept constrain, to have a user supplied concept that then constrains your library code. And I was annoyed by that writing this. Someone please write me a paper. So let's write some constructors. We're going to do our default just so that we can do, vector brace brace. That's a really nice feature, and we get it with a line of code. So I'm also, my highlighting got wonky. I have a storage function here. This storage function just goes and gets the vector by type. We've done this a bunch of times. I just got really sick of typing get t vectors. I wanted to type something just t. So that's why this exists. You're going to see that a lot in the next, 6 slides. So remember what that means. So let's do our next most basic constructor, right? We take 2 iterators. They have to be the same type. And then we want to store that to, man, why did this highlighting get weird? Okay, mental note. We want to store that to our underlying container, right? So we have to figure out which of the vectors in our tuple we want to access. Oh, sorry, forgot to mention, we're using the same tuple of vectors approach that we just used. We have to figure out which of the the vectors in our tuple we want to access. We can do that by using the value type of the iterator. We also want to make sure that the iterator type is the same as one of the supplied types. So here your user is going to explicitly supply a list of types that this vector is going to hold. I think it's worth noting that you could definitely do this with requires on the template. It ended up having to type name input it value type a bunch of times, and I got annoyed with that, so I switched it to a static assert. I don't know if one or the other is better, but they're both available. From there, we do the easy thing. We just get the vector using our storage class that everyone needs to remember. And then we start at the beginning of that vector and just insert from first to last, and we're done. Oh, not that one. There we go. So now we're going to do one more constructor, and that's the constructor where you provide a count of the number of elements that you want to insert, and then they all get the same value. So we're going to use our storage function again. We're going to go ahead and reserve the number of count just for performance reasons, and then we're going to push back n times. Pretty straightforward. But to do this, you may have noticed we use size type. And we have to be a little bit careful in how we get that, because we've got all these underlying size types, and we want them to, we need to make sure that we have some coherence there, right? So size type here is just assigned to be the first vector size type, which makes sense as long as you say that the first vector size type is the same as all the other size types. And this same as all is just a concept. It's the same concept as the same as any from before, but with an and instead of an or. I didn't include it on the slide because I didn't have room, but hopefully that's all pretty clear. So now we've got our vector and we're constructing. So let's do some of the easy operations here, right? Some of the stuff that basically comes for free. So pushback is exceptionally easy. We take a type, we constrain it on same as any. We're following all our best practices that we've established to this point. And we use that type, which, like the type has been deduced, right? So the user doesn't need to explicitly specify it. And we push back to the vector that holds the elements of that type. Popback is a little bit different because popback doesn't take an element, we can't deduce the type. So to pop back, the user does have to specify the type. This maybe doesn't make sense, right? Like the user has to be thinking of this, for this to make sense, the user has to be thinking of this as a loose collection of objects. And so that popback mechanism can't remove the most recent, it can remove the most recent of a type. Again, whether or not that makes sense is going to come down to your requirements. I decided that for this, we're thinking of things more as a loose collection of types, like I think Charles said earlier, more along the lines of an entity component system, where we're interested in, things of a particular type at any given time, and not the collection as a whole, for the most part. And then swap. Sorry, go ahead.
John, I would observe that the same limitation applies to in place back, which may be on the future slide.
Oh yeah.
And also users have to say .template pop back and .template in place back, which is a bit annoying.
Oh yeah, that's a good point. Yeah, that annoying bit of syntax could do with going away. So swap here, I included this one because I thought it was interesting to deduce the type of the vector from the internal type, from the type of the passed in vector, and not from the the type of like the whole type, but the partial type. Again, I think there are design decisions to be made here, right? If I say swap and I give you a vector that's of a single type, do you want to just get rid of, do you want to swap out just that type? Should we clear the other types? These are all things that you would have to decide based on your use case. I think here, if we're thinking of it as a loose collection, makes perfect sense to say, hey, you know, here's all my old things of that type, like, you know, put them, you know, flip flop them for me. And, you know, you come out of that, you know, with a pretty clean, coherent interface.
Do you think the name swap is good for that? Because shouldn't swap be swapping a not a stood vector, but your vector of
Like a multi-type vector.
A multi-type vector.
Yeah, that's a fair observation. You could even make an argument that like they could both exist and both be called swap, I think. I'm interested to know what people think. Like you could totally do that, as you say. I don't know if there's a different semantic and you might want to put it under a different name than swap. Yeah, it really depends on the semantic that you're trying to, like, what is this trying to capture, right? And I don't think, I haven't seen anything like this in existence. So I don't know if of anything to pull on for inspiration here. So I was kind of shooting from the hip with some of this. But
I see this code and I think it's like you're wanting to go through a list of things, and some of those things you want to do something to them. Like here, you're swapping out all of the things that match a specific type. I mean, I'm just imagining you had a vector of a T where the T has a enum inside of it, and you wanted to replace all of the enums of a certain type or a certain value. And that's what this is in a sense equivalent to, abstractly speaking, not concrete. But
yeah.
the word swap does not like mapped in my head to that kind of action.
Maybe this is actually called swap type.
Yeah, swap types.
I think that like the observation that this the utility of this this class is really down to how you're using your types is especially salient, right? If you want like a single collection of things that you're generating things and you don't know what type they're going to be when you generate them, but when you access them, you're going to want or be okay with accessing them one type at a time. This works great. If your usage pattern is the opposite of that, we've made a lot of bad design decisions here that are going to, really get in your way and make things difficult. All right, let's do some things that act on more than one of the underlying vectors. So the easy case here is clear, right? If you say clear, you want to clear everything. We can just do a stood apply over all the vectors, call clear on each one. We're done. There's also another case here where you potentially want to do a stateful operation. So size is a great example of that. If you want to sum all the sizes, you have to take some state into your size function, just add those together, return your total size. I think those are pretty clear.
I can only see a size being helpful if you're able to access the individual arrays or individual vectors underneath it.
I could see it being useful for debugging or something like that.
Maybe debugging. I just imagine the times I'm actually wanting to call the size is when I'm passing the vector into like a C API or some other container that needs to have access to the elements, using the .data.
Yeah, and specializations of these on a single type are trivial, right? Like we could have gone through and done the same thing as we did here for both of these if you wanted a more focused one. Like I said, I'm kind of cherry picking the operations that I thought were interesting rather than being exhaustive here, because no one wants to hear me say the same thing like 6 times in a row.
How do you
I don't
know
think
if
this
it's
is how
safe
stood
to
apply
pop?
works.
Oh,
Sorry.
Just
You go first.
Okay. How do you know if it's safe to call pop on a certain type?
You would need to do that from context, I suppose. I don't have a great answer there. Fair point. you could, if you had a typed size, right? If that were important to you, you could have a typed size that would make it easy to do that.
And how do you iterate through all the items in the same order that you push them in?
So you want the order of items in the vector absent of their type information?
Yeah, so for example, I have three different types in that vector. I pushed type A, then type B, then type B, and then type C. And I would like to go through, from the 0th element to the nth element and get A, B, B, and C, or, A, B, C, or whatever.
So if that use case is important to you, this is not the right container to select. If you wanted to change this particular container to do that, you would take the vector of variance pattern. At that point, I think you probably just do a vector of base class. Again, broadly, I would say if you have that access pattern, it may be worth considering your architecture and whether or not you can make it less dependent on the ordering across types. There are certainly domains where you must depend on that ordering, but
yeah, here's the parallel for whatever I think Jason was talking about in regards to CAD applications where you need to draw in certain order and you have different objects underneath it, right? And here virtualization is very helpful.
Yeah, and I like, again, I don't think that I wouldn't make the argument that no one should be using virtual. The argument here is
I'm not saying that you're making that argument, right? I'm just asking if this is, if you envision such possibility using this thing, this construction.
Yeah, I don't know enough about GUI programming or like CAD software to really offer much in the way of an opinion there without a more constrained question. Certainly I'd be happy to talk about, if you can boil it down to like a simple design. I'd be happy to talk about how you can, twist that design to be less dependent on type ordering. But I just don't have the domain knowledge there.
I will say, just for the sake of argument here, I do know that there are user interfaces that are entirely known at compile time that that manage to avoid virtual and do GUI development at the same time.
Thank you.
So, John, I don't think this code is correct because apply, the function you pass to apply needs to take the tuple will be unpacked and passed as all of the arguments.
Yes, you're correct.
So you'll need to, yeah. I mean, the intent is clear, and these will work, but they're just not quite correct as written.
Yeah,
I think size gets simpler because you can just return the value of std apply.
Yeah, that was lost in translation from not slideware to slideware. All right, we've got two more examples, and they're the ones that I think are actually the most fun. Before we talk about InPlaceBack, I want to talk about the InPlaceable concept because I think it's important to understand upfront. So we've got a concept InPlaceable. It takes the type of a vector and then a pack of args, and then we see if we can InPlace back into that vector type with those argument types. Does everyone feel comfortable with that? Anyone unclear? All right, awesome.
I don't feel terribly comfortable with it, but I'll ask my question in a minute.
Okay. So for InPlaceBack, we really don't want to have to take the type of the vector if we can avoid it, right? And in general, in this interface, if we can avoid taking the type of the vector, that's great for a number of reasons. So we're going to take just the args, right? And then we're going to check if any of the vectors, if we can InPlace back into it with the supplied args.
That might add multiple items, right? Because you don't have an escape clause in here.
sorry, I'm not sure I follow.
If multiple types in your set have constructors that match the set of parameters that you passed in, then you will construct an object for each of those types because you never return. You don't break from this if const expert in any way.
So that's what the static assert is for. So the concept.
Oh, okay. I see. You only allow
Here,
one.
yeah.
Sorry.
So here the
Got it.
concept in placeable evaluates to a Boolean. Num true is the dumbest function I've ever written. It just adds together a bunch of Boolean numbers. And exactly one of them must be true. There are better ways of doing this, but this was the one that would fit on slides. In fact, I would argue that if you wanted to implement this for real, there should be two static asserts. You should have one that says that your number of true is not 0 with one error message that you couldn't find a type that you could construct with those args, and then a second one that says that it's less than 2 or however you want to say that. And if you're and that error message would be that you found multiple types, because those are very distinct cases. I was really short on lines on this slide, so I collapsed them into one. But in reality, and then we have the same stood apply error here, but the concept carries through, right? We take our vector, we design by introspection. We check if it's implaceable. We found the one that we want. We emplace back. That forward is just a forward macro. I'm sure you guys have that in your code base. And here we've safely emplaced back, right? Any questions there? This is a dense slide.
Why is the lambda templated?
It's templated because I need the type of the vector. You could do a decal type on vec, but then you have to decay it.
Yeah, it's just an easy way to be able to spell tvec. Introducing it in the template head.
I'm
Go ahead.
I'm just nitpicking. I think the implaceable wouldn't work if a constructor takes a non-const value reference.
Yeah, there's probably a case there where
I think it would, because
oh no, yeah, because
effectively inside the function.
Yeah, in placeback specifically, there's only an overload for our value reference.
Well, they're universal references.
Yes,
but the requires clause effectively acts like you're inside a function, and the targs coming in are named, so they're L values effectively inside the function, I think. But I have a different issue with line 3, which is that it's testing that you can write that syntax, and whether or not that's true, like you can call in place back with anything because it just takes a pack of universal references, and the compiler would have to instantiate the function or do something to figure out whether that will compile. And I don't know when that happens in checking a requires clause. In particular, I don't know if it'd be different if there were a trailing return type on in place back, for example.
Yeah, you actually want to test the constructor call of that type of tvec instead of implaceable, huh?
I thought that the I wrote these last couple of slides somewhat quickly, so I didn't test this as thoroughly as I would have liked. But I thought that I thought that tvec was instantiating the constructor underneath and checking that syntax on line 3. But I will definitely look into that.
Like I would hope that that's the case, but I fear that I fear that the concept would pass, but then when the function was instantiated, it would produce a compile error later. Like imagine if in place back. Yeah. For example, I don't know exactly what happens here, but I feel like I've run situations where, let's say, in placeback has a trailing return type on it. The compiler kind of just looks far enough to know that, oh yeah, you can call that, and I know what it will return, kind of thing. But it doesn't actually instantiate the function template all the way down, and then so the concept will pass, and then when you actually call it, it would cause a compile error.
I would expect that.
Admit, I don't know
because the
too well.
The type of tvec includes its the value type there necessarily, right? But because you need it to name that type. I would expect that would work, but I'll definitely investigate that. Any other questions on this slide? Cool. Okay, let's talk about insert. So this one gets into kind of a fun design discussion. So I'll just say before anyone jumps ahead of me, I don't think that this actually works very well, given the code that we've covered so far. So insert, you take some position, right, and then two iterators. We do the same thing that we did in the constructor to get the value type and make sure that we can hold it, and then we go and we insert, right? But here we have a return type, right? And we also have position. Position, as written, has to point to an iterator into the vector that you're trying to insert into, which we haven't supplied the user any way of getting. And similarly, the return type is an iterator into that, whatever container they select, right? So if they somehow manage to get it and call this, they get an iterator into a thing that we're like functionally trying to keep private here. So I think there's like a really interesting design discussion to be had here around like, maybe you implement like a custom iterator type that, spans all of the, all of the types in like the order they're declared. And that's how you implement this functionality. Like there's a number of approaches that you could take. And I think as if you want to pursue this sort of approach, you have to consider those sorts of design decisions, and ask yourself if it's worth the complexity, right? Now to implement this, we have to go and implement, if we wanted to take that approach, right, we have to implement a whole custom iterator, which is not simple, on top of all of this, the complexity of a multi-type vector, where we could in fact just use the virtual keyword a couple of times, hold a couple pointers, and have a working interface, a working application that would likely be a lot simpler for new developers to understand, for example. So I think there is potentially a too far for this. As you guys have kind of observed throughout the presentation, there's a point at which in certain domains this gets really difficult to do, and you should ask yourself, like, does it make sense for us to really travel down this path, or are we inviting terror? Yeah, anyways, that's my presentation. Thanks for the really thoughtful, insightful commentary, guys. This went way better than I thought it even could. So
Thank you.